Okay, welcome everybody to another episode of Keenan Can Do. If you remember yesterday, we left off with Chapter 6, finishing up Chapter 6, which is introduction to the C programming language. Very cool chapter. I recommend if you have questions, go back and look at that. Talked about the different types of the C programming language, versions, the different standards. And then we saw a couple examples of things. And we saw that we do actually have access to find the notes for the programming language exercises when we want to use those. So today we're going to continue on with Chapter 7, which is integer types. And I did get the chat set up. I hope, let's do a test to where it looks like, yeah, overlay. So you should be able to see the chat overlay inside of the YouTube chat inside of the view here. So let me know if that's well readable, or if I need to change the text or the CSS or anything like that. Can you read this? Okay. Okay, sweet. So without further ado, we will let's go back to this chapter. Let's create a chapter 7. I don't remember how to create a directory. Dirid, create directory, new directory. Do I just hit plus? I think I just hit plus, if I remember correctly. So if I just hit plus, yeah, and directory, we'll name it chapter 7, of course. All right, so we're in chapter 7 and there's nothing there. So let's start. Integer types in C. Most variables in C programs tend to hold integer values, and indeed most variables in C programs tend to be the default integer type int. Declaring a variable to have a particular integer type controls how much space is used to store the variable. Any values too big will be truncated, and specifies that the arithmetic on the variable is done using integer operations. Basic integer types. The standard C integer types are char, short, int, long, and long. The typical size is for architectures like the Intel x86, which is the architecture used in most desktop and server machines. Some 64-bit machines might have 64-bit ints and longs, and some microcontrollers have 16-bit ints. Particularly bizarre architectures might have even wilder sizes, but you are not likely to see this unless you program vintage 1970s supercomputers. The general convention is that int is the most convenient size for whatever computer you are using and should be used by default. Oh, sweet. Thanks, David. Cool. That's cool. That's better interaction with the streamers then. Many compilers also support a long type that is usually twice the length of a long, making it 64 bits on x86 machines. This type was not officially added to the C standard prior to C99, so it may or might not be available if you insist on following the ANSI specification strictly. I'm noticing that my mic is pretty loud. Is it the right mic? Okay. How does my mic sound? Do I need to turn it down? Okay. Sounds good. Let me see. Can I monitor the mic? I don't know if I can monitor the mic. Let's see. Microphone. Okay. Oh, yeah. You can monitor the mic. Although that does sound kind of weird. It doesn't echo for you guys, does it? I'm hoping not. Let me turn the monitor off. Okay. All right. Many compilers also support... Good. Thank you. One moment. Oh my god. I wanted to send a heart, but it said that I have to... No, no, no. The echo shouldn't be happening like that. Oh man. Hold on here. Okay, there we go. There we go. Okay. No. It was weird. Okay. Many compilers also support a long type that is usually twice the length of a long, making it 64 bits on x86 machines. This type was not officially added to the C standard prior to C99, so it may or may not be available if you insist on following the ANSI specification strictly. If you need to know the exact size of each type, you can use the size of operator, which returns the number of chars in a type. For example, on a typical machine, size of int will evaluate to 4, and size of long will evaluate to 8. You can multiply by the constant char bit, usually defined in limits.h, to translate these numbers to bits. However, if you are looking for a type that holds a particular number of bits, you are better off using a C99 fixed width type like int 32_t. Okay, let us try that. So first off, let's see if we have limits. Let's see, info limits. Nothing. Man limits. Is limits? Oh, it's right there. Limits. That's not where standard SDI. Yeah. Limits. Info. Lib. Info limits. Info limits. Less limits. Push the limit. That's funny. Maximum length of any multi-byte characters. Okay. So it's just a bunch of macros. Okay. All right. So let's do that. We'll do like, I don't know, size. Size.c. We'll include input.h, and then let's include that limits. Okay, and then we'll do an int main void, and then let's just do printf size of int is int d and size of int okay, return 0 if this compiles. 3, 0. Too many arguments for format. Oh, %D isn't the right one, huh? Let's try compile again. Oh, thank you. Oh, man. So, format D expects type of type int, but argument 2 has type long unsigned int. Int long unsigned int. Oh. What is the format for long unsigned int then? And put that H. Info. That H. Print F. Long unsigned. Do you know time may preceded by unsigned decimal? Input range. Wait a second, wait a second. Oops. Print F, yeah. No. And H. Wait, so that's not the C print function. So wait a second. How do I man SDIO? Okay. Info SDIO. Info SDIO. There we go. There's printf. Okay, so now I search for unsigned. Following integer components are short. Unsigned long. Okay, L. That's it? That's it. That's all we needed was L. Okay. L. At least we're learning. What? Conversion lacks type at the end of the format. So did it run? Size of int is nothing. Okay. I'll get to that. I mean, this is... I don't understand why it's not working. Size of int is nothing. Size of int is function. Warning: conversion lacks type at end of format. Conversion lacks type at end of format. That's not the type? Oh. Okay. I see now. You need to do D. I think that's it. No. Specs argument type int, but argument is type long. Too many arguments. Convert. Let's try. Huh. I don't know. We'll look at that later. If you need to know the exact size of each type, you can use the size of operator, which returns the number of chars in a type. For example, in a typical machine, size of a value to 4 and size of long value to 8. You can multiply by the constant char bit. Usually find you as include limits. I need to, my apologies. I need to start talking more. I should have been talking when I was doing it. To translate, however, you're looking for a type that holds particular, each of these comes in signed. I want to know what's going on here, though. I don't want to kill. Meta W. Okay. Yeah, meta W. Excuse me. Oh, oops, it's this one. End of format. Yep. Okay. You have extra blank between field width and type, for example. is not valid. It should be without extra. Parameter flags with precision length. But is it? No, it's not. Didn't print it. Okay. If you need to know exact size of each type, you use it. Each of these types comes in signed and unsigned variants. This controls the interpretation of some operations, mostly comparisons and shifts, and determines the range of the type. For example, an unsigned char holds values in the range 0 through 255, while a signed char holds values in the range -128 through 127. And in general, an unsigned n-bit type runs from 0 through 2n-1, while the signed version runs from -2n-1 through 2n-1 The representation of signed integers uses 2's complements notation, which means that positive value x is represented as the unsigned value x, while a negative value x is represented as the unsigned value 2n-x. For example, if we had a peculiar implementation of C that used 3-bit ints, the binary values and their interpretation as int or unsigned int would look like this: 0, 0, 1, 1, 2, 2, 3, 3, 4, Okay, I'm not sure I'm understanding this quite yet. Let me look in here. It's DIO. Which should be used to compute the size of its operand. The result of size is of the unsigned integral type, which is usually denoted by size t, that size of. Is that the LU? Okay. Do we have to do LU? Because is that the part that does the unsigned? But it didn't tell me that. Okay. Printf. Decimal, integer, O, U, X, or X. Okay, so that one's finished. Four. Why? Okay. Okay, so representation sign introduces 2's complement, which means that a positive value is x is represented as unsigned value x, while a negative value, negative x, is represented as the unsigned value 2n minus x. For example, if we had a peculiar implementation of C that used 3-bit ints, the binary values and their interpretation as int or unsigned int would look like this. Unsigned 0, 1, 2, 3, 4, 5, 6, 7. Okay. As that's unsigned. As signed or int 0, 1, 2, 3. We get one extra negative value for assigned integer type is this allows us to interpret the first bit as the sign, which makes life a little easier for whoever's implementing our CPU. Two useful features of this representation are we can convert freely between signed and unsigned values as long as we are in the common range of both. In addition, and subtraction work exactly the same for both signed and unsigned values. For example, on our hypothetical 3-bit machine, 1 plus 5, represented as 001 plus 101, gives us 111 110 gives the same answer as 1 plus negative 3. 001 plus. In the first case, we interpret 1106, while in the second, we interpret as negative 2, but both answers are right in their respective context. Okay, so the first bit is the sign. Oh, okay. So that would be negative 4, that'd be negative 3, that would be... Note that in order to make this work, we can't detect overflow. When the CPU adds two 3-bit integers, it doesn't know if we are adding 7 plus 6 equals 111 plus 110 equals 1100 equals 13, or negative 1 plus negative 2 equals 110 plus 110 equals 101 equals negative 3. In both cases, the result is truncated to 101, which gives the incorrect answer 5 when we're adding unsigned values. This often can lead to surprising uncaught errors in C programs. Although using more than 3 bits will make overflow less likely, it is usually a good idea to pick a size for a variable that is substantially larger than the largest value you expect the variable to hold, although most people just default to int. Unless you are very short on space or time, larger values take longer to read and write to memory and may make some arithmetic operations take longer. Taking into account signed and unsigned versions, the full collection of integer types look like this: char, signed char, unsigned char, short, unsigned short, int, unsigned int, long, unsigned long, long long, unsigned long long. So these are all examples of declarations of integer values. Int I, char C, signed char temperatures, degrees Celsius only valid for Earth's surface. Signed char temperature, long net worth in pennies, long Bill Gates net worth in pennies, unsigned short, shave and haircut 2 bytes. This can often lead to surprising uncaught. So I'm still not understanding why. The reason we get one extra negative value for a signed integer type is this allows us to interpret the first bit as the signed, which makes life a little easier for whoever's implementing. 2 useful features. We can convert freely between signed and unsigned values as long as we are in the common range of both. And addition and subtraction work exactly the same for both signed and unsigned values. For example, on our hypothetical 3-bit machine, 1 plus find represented as 001, and 101 is 110 gives the answer 110 is 6 or negative 2. One plus negative 3. In the first case we interpret a 6, while in the second we interpret but both answers are right in the respective contexts. Unsigned. So okay, so if it's a 3-bit, then only 2 bits are, so that'd be 0, 1, 2, 3. First bit is the sign. Negative. But that's 1 and 1. That'd be negative 2. For chars, whether the character is signed negative 128 to 127 or unsigned 0 to 255 is at the whim of the compiler. If it matters, declare your variables as signed char or unsigned char. For storing actual 8-bit characters that you aren't doing arithmetic on, it shouldn't matter. There is a slight gotcha with character processing with the input functions getChar and getC. These return the special value end of file defined in .h to be -1 to indicate end of file, but 255, which represents Y in the ISO Latin 1 alphabet and in Unicode, and which may also appear quite often in binary files, will map to -1 if you put it in a char. Yes. Yes. So you should store the output of these functions in an input, in an int if you need to test for end of file. After you have done this test, it's safe to store a non-end of file character in a char. Right, int c, while c is get char not equal to end of file, put char c. Wrong, char c. While c is equal to get char not equal, don't do this, put char c. Put these functions in an int if you need to test for end of file. After you've done this, save. After you've done this test, it's safe to store a non-end of file character in a char. Overflow in the C standards. So far, we have been assuming that overflow implicitly applies a mod 2b operation where b is the number of bits in our integer data type. This works on many machines, but as of the C11 standard, this is defined behavior only for unsigned integer types. For signed integer types, the effect of overflow is undefined. This means that the result of adding two very large signed ints could be arbitrary, and not only might depend on what CPU compiler options you are using, but might even vary from one execution of your program to another. In many cases, this is not an issue, but undefined behavior is often exploited by compilers to speed up compiled code by omitting otherwise necessary instructions to force a particular outcome. This is especially true if you turn on the optimizer using the -0 flag. This means that you should not depend on reasonable behavior for overflow of signed types. Usually this is not a problem because signed computations often represent real-world values where overflow will produce bad results anyway. For unsigned computations, the implicit modulo operation applied to overflow can be useful for some applications. C99 provides a standard int.h header file that defines integer types with known size independent of the machine architecture. So in C99, you can use int 8_t instead of signed char to guarantee a signed type that holds exactly 8 bits, or uint 64_t instead of unsigned long to get a 64-bit unsigned integer type. The full set of types defined are int 8_t, int 16_t, int 32_t, and int 64_t for signed integers, and uint 8_t, uint 16_t, uint 32_t, and uint 64_t for unsigned integers. There are also types for integers that contain the fewest number of bits greater than some minimum. Example, int _least 16_t is a signed type with at least 16 bits chosen to minimize space, or that are the fastest type with at least the given number of bits. Example for this is int _fast 16_t is a signed type with at least 16 bits chosen to minimize time. The standard int h file also defines constants given the minimum and maximum values of these in standard integer types. For example, int min and int max give the smallest and largest values that can be stored in an int. All of these types are defined as aliases for standard integer types using typedef. The main advantage of using standard int.h over defining them yourself is that if somebody ports your code to a new architecture, standard int.h should take care of choosing the right types automatically. The main disadvantage is that, like many C99 features, standard int.h is not universally available on all C compilers. Also, because these fixed width types are a late addition to the language, the built-in routines for printing and parsing integers, as well as the mechanisms for specifying the size of an integer constant, are not adapted to deal with them. If you do need to print or parse types defined in stand.int.h, the larger int types.h header defines macros that give the corresponding format strings for printf and scanf. The int types.h file includes standard int.h, so you do not need to include both. Below is an example of a program that uses the various features provided by int types.h and standard int.h. Okay, we're line 1, including standard input output.h, standard lib.h, and then assert.h. And then int types.h, example using fixed width types. Largest value we can apply 3x plus 1 to without overflow. Define max value uint64 minus 1 divided by 3. Largest value we can apply 3x plus 1 to without overflow. Int main int argc char uint64 underscore t big. Usage number. Parse argv as uint. scnu64 expansive format string. Do some arithmetic on big. While big is not equal to 1, PRU expansive format string for printing. Printf percent PRIU64. What in the? And big. If big. Where's PRIU? PRU expands to the format string for print in uint64 underscore t. Oh. PRU big. Okay. Percent. And that expands somehow. I don't understand that yet. Okay. Size t and PTR diff t. The type aliases size underscore t and PTR diff underscore t are provided in standard def.h to represent the return types of the size of operator and pointer subtraction. On a 32-bit architecture, size t will be equivalent to the unsized 32-bit integer type uint32t, or just unsigned int, and p pointer diff underscore t will be equivalent to the signed 32-bit integer type int32 underscore t. On a 64-bit architecture, size t will be equivalent to uint64 will be equivalent to, and then pointer diff underscore t will be equivalent to int64 underscore t. The place where you will most often see size t is an argument to malloc, where it gives the number of bytes to allocate. Because standard lib.h includes standard def.h, it is often not necessary to include standard def.h explicitly. Okay. Integer constants. We have a lot more to go. Okay. Constant integer values in C can be written in any of 4 different ways. In the usual decimal notation, egg 0, 1, negative 127, 9999. In octal or base 8, when the leading digit is 0, egg 0, 1 for 1, 0, 1, 0 for 8, 0, 7, 7, 7 for 5, 11, 0, 1, 4, 1. Octal is not used much anymore, but it is still conventional for representing Unix file permissions. In hexadecimal base 16, we're prefixed with a 0x. The letters A through F are used for the digits 10 through 15. For example, 0x61 is another way to write 97. Digits 10 through A through F. Six and 1 is another way to write 97. How is that? Base 16 when prefixed with oh. Because that would be six 16s? I don't. 96. Okay. So 6/16s, right? Because this is 6/16s. And then plus one of... Yeah. Okay. That makes sense now. Using a character constant, which is a single ASCII character or an escape sequence inside single quotes. The value is the ASCII value of the character. A is 97, unlike languages with separate character types. C characters are identical to integers. You can but shouldn't calculate 972 by writing A times A. You can also store a character in a location with any integer type. You can also store a character in a location with any integer type. Okay. Except for character constants, you can insist that integer constant is unsigned or long by putting a U or L after it. So 1 UL is an unsigned long version of 1. By default, integer constants are signed ints. For long constants, use long. Example, the unsigned long constant x dead beef. It is also permitted to write L as L, which can be less confusing if the L looks too much like a 1. Aha. A int, 97 int, 97U, unsigned int, bead full, unsigned int, unsigned long written in hexadecimal, 077S short written in octal. A curious omission is that there's no way to write a binary integer directly in C. So if you want to write the bit pattern 1, 2, 5, 11, you would need to encode it in hexadecimal as 2D. So A, B, C, D, E, F. 2, so 32. 2. Plus 32 plus A, B, C, D, 4, so 14, 46. Another potential trap is that leading zeros matter. Okay, so what is this in hexadecimal? That should be, I was guessing 46, but I don't know. 45. So I was one off. 13. So that means we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D. It is 14. What? Ten through 15. Okay. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D. 9, 10, 11, 12, 13. Ah, it is 13. Okay. So that is 45 in hexadecimal. Very good. Very good. Another potential trap is that leading zeros matter. 0, 1, 2 is an octal value representing the number most people call 10. Yes. Another potential trap is that leading zeros matter. Oh, yeah, because that's octal, because that is 0 16s, 1 8, and 1 2 1s. Very interesting. Okay, I think I'm getting the... Very interesting to get a handle on the octal and hexadecimal stuff. Naming constants. Having a lot of numeric constants in your program, particularly if the same constant shows up more than one place, is usually a sign of bad programming. There are a few constants like 0 and 1 that make sense on their own, but many constant values are either mostly arbitrary or might change if the needs of the program change. It's helpful to assign these constants names that explain their meaning instead of requiring the user to guess why there is a 37 here or an there. This is particularly important if the constants might change in later versions of the program. Since even though you could change every 37 in your program into a 38, this might catch other 37 values that have different intended meanings. For example, suppose you have a function call it getChar that needs to signal that sometimes it didn't work. The usual way is to return a value that the function won't normally return. Now you could just tell the user what value that is. Return -1 on end of file, and now the user can write, well, c.getChar is not equal to -1, but then somebody reading the code has to remember that -1 means end of file and not signed version of FF or computer room on fire, evacuate immediately. It's much better to define a constant end of file that happens to equal -1, because among other things, if you change the special return value from getChar later, then this code will still work, assuming you fix the definition of end of file. So how do you declare a constant in C? The traditional approach is to use the C preprocessor, the same tool that gets run before the compiler to expand out include directives. To define end of file, the file includes the text, define end of file -1. What this means is that whenever the character EOF appear in a C program as a separate word, example in 1 plus EOF, but not in a parenthesis there EOF, then the preprocessor replace them with the characters -1. The parentheses around the -1 are customary to ensure that the -1 gets treated as a separate constant and not as part of some larger expression. So from the compiler's perspective, end of file really is -1, but from the programmer's perspective, it's end of file. This is a special case of the C preprocessor's macro mechanism. How do you declare a constant? In general, anytime you have a non-trivial constant in a program, it should be defined. Examples are things like array dimensions, special tags or return values from functions, maximum or minimum values for some quantity, or standard mathematical constants. For example, math.h defines m_pi as the mathematical chi to umpteen digits. This allows you to write char buffer max file name length +1 area equals m_pi r squared if status is equal to computer room on fire evacuate instead of char buffer 513 area is 3. Not the correct value of pi if status is equal 136 evacuate, which is just an invitation to errors, including the ones in the area computation. Like type defs, defines that are intended to be globally visible are best done in header files. In larger programs, you will want to include them in many source files. The usual convention is to write define names in all caps to remind the user that they are macros and not real variables, because they're constants. Yeah, because they're constants. So now we're in operators, logical operators, relational, converting to and from strings. Okay, so I did do a couple exercises up to this point. Let's see. So I had ChatGPT actually. What I did is I asked ChatGPT. So what I did, this is what I did. I said, hey, I'm learning to program in C. Create me a prompt that would instruct you to navigate a chapter located on a website, read the text, and then generate 5 to 10 exercise questions for programming practice without giving the answers to the questions. Certainly, here's a sample prompt you can use. So then it created me the prompt. So now I have the prompt that I want. And now, let me actually save this prompt. In my C programming prompts. Let's just do it here. Okay. So now I have the prompt. Okay, and then I went to a new chat and I asked it. At first, it was like, I can't do it, and then it did it. So, so the question for number 1 is saying, identify the integer types, list the basic. So that we could do, the first 3 tonight. It's getting kind of late. I need to go see my family for a little bit here. Oh, let's just do the first 1 today. So the first one is this one right here. So we'll do that one. Yank. Oops. Oh no. Oh no. I killed Emacs again. Save buffers. Remember when I did that last? Gotta remember, Control Z is not your friend when you're in Windows. I'm thinking about switching back to Linux again very soon. Okay, so let's copy that again here. Copy, and then okay, and then set with fundamental. Okay, text mode. Okay. So the integer types, this is the basic integer types. So we have 1's char, 2 is int, 3 is oh, and then I need the size. Char 4, int 8, long is 32, I believe. 4 is, what else we got? I think I got those right. Let's see. Char is 8. Oh, char is 8. Int is 32 by default. Long would be 32. Long is 64. And then this depends on sign. If it's default signed or not. So 8. Int long. Int short. Oh, short is 16 bits. Oh, I forgot about that. So I'll do them again tomorrow too. So short 16. 3 int is 32. 4 long is 32. 5 long is 64. Okay, so let's see. Question answer to 1. Okay. Let's do number 2, understanding overflow. Understanding overflow. Overflow occurs when you are using signed types and you attempt to assign a value that would work with an unsigned type, and thus you end up with an overflow. An example of this is signed char would make value 255 overflow to -1, while unsigned char would assign the value of 255? What I think, we'll see. Answer to 2. Question 2. Answer. Oh, yeah. But how did the standards address it, as you asked? Oh, okay. So I did a decent job with my explanation. Okay, cool. And then part 3 is usage. Write a C program to display the size of each basic integer type using the size of operator. Q3. Let's do include H. We'll include the header. We'll say int main. We'll do void with it, and we'll say that we're gonna have a char t equals t, and then we'll have a short me equals 15, and then we'll have a int mine equals that much. Then we'll have a long big equals that much. We'll have a long biggest equals that much. Hope that works. Okay, and then we will print f char size is percent LU? No? Yeah, because that's N short size is percent LU N long size is percent LU N long size is percent LU N, and then we have char short. So size of Big. Size of biggest. Make. Char size is 1, short size is 2, long size is 4, long size is 8. Why can't I? What is? Oh. Okay, cool. That's why we didn't have it. Size of short. Okay, guys, we will pick up on the integer operators on the next stream. That's it for today. Thanks everyone for joining. We'll chat later. This is Keenan Can Do, and I'll see you later.